my computer, then let's see, share screen. So far, so good. Now, okay, good. Today it connected without any hassle. That's the good thing. Yeah, Blackboard is on eCampus. That I know, but I wasn't sure whether you can use it. I mean, is it if it's as flexible as Zoom or not? But I mean, you were saying that it is, so well, if something happens, we can switch to Blackboard then. Okay, anyway, so the plan for today is to do a bunch of problems on diagonalization and then switch to, maybe at the end of the class, switch to the second part of the course, that is vector calculus. Okay, so by bunch of problems, I mean that I will select some problems from, let's see which note we are in. Oh, just a moment. So we are in note, let's see, note 11 for the moment. So I'll select a bunch of problems from note 11 and 12 and just solve it to show how things work and then move on to vector calculus. Okay. So right now we are in note 4. So I don't, so which class are we right now? 4, 5, I think class 6 maybe. Okay, so the first problem, so we are now in note 11, that's what I said, right? Note 11. So this is eigen 4. And we are solving problem 2.5. Why I named it 2.5, I don't know. Maybe because it's in between 2 and 3. So I added it later. Anyway, so this is 2.5. It's fairly simple. So you have this matrix A, 2 minus 3, 2 minus 5. So the question is diagonalize. Diagonalize A. And once you are given this sort of problems, this covers almost everything about eigenvalues, eigenvectors. To diagonalize, as you have seen, you need the eigenvalues, you need the eigenvectors. Then and only then you can guarantee that something is diagonalizable. So, I mean, problems in exam could directly be from diagonalization so that it tests you on everything. Yeah, so the first thing, so step 1 is find eigenvalues and eigenvectors. Vectors, so the characteristic polynomial 2 minus lambda minus 3, 2 minus 5 minus lambda. So this is lambda minus 2, lambda minus 5 plus 6. And you want to find the roots. So the two eigenvalues are lambda 1 equals 1 and lambda 2 equals 4. So at this point, once you have the eigenvalues, can you tell me whether this matrix is diagonalizable or not before moving forward at this point? There is one result that we, or one fact which we did in the last class. So what happens if n cross n matrix has n distinct eigenvalues? Any ideas? So it has n distinct eigenvalues and it's an n cross n matrix. So we did a fact, and I think it follows from the fact that the matrix has to be diagonalizable under such scenario if it has n distinct eigenvalues. So here we have a particular example. So this is a 2 cross 2 matrix and we have 2 distinct eigenvalues. So at this point, since the eigenvalues are distinct, we can say that A is diagonalizable. What's more, you can even write down the diagonal matrix. So the diagonal matrix is given by writing out this eigenvalues as the diagonal elements, and of course 0 everywhere. So this is the D. Now to find P, we need the eigenvectors. Okay. Now it's a straightforward problem. So E of 1, so this is the null space of A minus just I2. And this is something I skipped the computation. So check that this is given by span of 3, 1. Okay, and E of 4, so this is the null space of A minus 4I2. So this will be span of, oh, just a moment. Sorry, so I think so there's a change of sign. So the eigenvalues are lambda 1 equals 1 and lambda 2 equals minus 4. So we have a plus sign here. So this is 1 and 2. Okay, so we have 2 representative eigenvectors for the 2 eigenvalues. Okay, and that's all we need. Now, then P is given by writing out this eigenvectors as the columns. So 3, 1 and 1, 2. Note that this writing out the eigenvectors as columns depends on how you wrote down D. So if you switch the eigenvalues, so for example, so let's do it. So to complete the problem, hence D is equal to, well, we have the specific D in this case. So 1, 4, 0, 0. So this is equal to, was it P inverse AP? Yeah. So 3, 1, 1, 2 inverse A times 3, 1, 1, 2. So this is one diagonalization, but it will also depend on how you write down the eigenvalues for the diagonal matrix. So if you write out 4 as your, rather minus 4, not 4, minus 4 as your first entry and 1 as your other entry, so you switch the diagonal elements, then accordingly, your matrix will change. So now the eigenvector corresponding to minus 4 would be the first column. So now you have 1, 2, and that for 1 will be the second entry. So the second column is given by 3, 1. And now you take the inverse times A times 1, 2, 3, 1. So this is another diagonalization. Okay, so there can be plenty of diagonalizations depending on how you arrange the diagonal entries. Okay, so this is a typical example. So you can get maybe 3 cross 3 matrices, but this is just the standard way to find out the eigenvalues and eigenvectors. So any questions so far? If not, then I will do number 4, which is for a 3x3 matrix, but it's exactly the same process. So A, well, let's see. I mean, there could be repeated eigenvalues, so things might be slightly trickier. But in principle, the process remains same. So this is our matrix now. So diagonalize A. Diagonalize A. Okay, so problems can be of 2 different types. Number 1 is of this type, diagonalize A. So then you have to find the eigenvalues, eigenvectors. So here a priori, you know that A is diagonalizable, and you need to find the matrices P and D, which diagonalizes A. Type 2 is something like this. So argue whether A is diagonalizable or not. So in that process, in the second type of problems, you can either actually argue using some facts that A is diagonalizable without actually finding the diagonal matrix or finding the matrix P. But if you are asked to diagonalize, then you have to find the matrices P and the diagonal matrix P. Okay, so here let's find the complete solution. So we need to diagonalize. So once again, let's find the eigenvalue. So the eigenvalues is given by the determinant of A minus lambda I3. Now, this is where I skip a few steps. The complete detail is done in lecture note. What I get, so there is a huge, I should say, huge step jump. This is completely worked out on the lecture note. So the polynomial is given by this, or with a minus sign. Okay, so this is the polynomial. And the eigenvalues are given by lambda 1 equals 0 and lambda 2 equals lambda 3 equals 1. Okay, so you have 2 distinct eigenvalues. So we have 2 distinct eigenvalues. One is 0 and the other is 1. So this has algebraic multiplicity 1, and this one has algebraic multiplicity 2. Okay. Now, the eigenvector corresponding to 0 is not a problem, because since eigenspace is a vector space, it should have dimension at least 1. So the geometric multiplicity for eigenvalue 0 should be 1. There's no problem. The problem might arise for the second scenario. Here, the algebraic multiplicity is 2. So you really need to find out, well, in this case, you need to find both the eigenspaces since you want to diagonalize. But if, for example, here you are given that argue whether A is diagonalizable or not, then the problem might arise for this particular eigenvalue. So this has algebraic multiplicity 2, and it might happen that the geometric multiplicity, which is the dimension of the eigenspace of 1, that might drop. Okay, so here you really need to work a little bit, but in this case, let's figure out both the eigenspaces. So E of 0, so this is simply null space of A. So this is null space of the following matrix. Well, the matrix A, that is, so 2 minus 1 minus 1. And once again, check steps. So this is given by span of this vector. So the in-between steps for the moment you know. So what you do is to row reduce this matrix and then solve for x, y, and z for the homogeneous system. So that's where I skip steps, simply because I have to reach up to a point. So this is given by span of this one vector as expected. So the dimension of E0 is 1, and we're good. Now E of 1, so this is the null space of A minus I3. So the null space of the following matrix: 2 minus 1 minus 2, then 2 minus 1 minus 2 once again. Wow, this is good. 2 minus 1 minus 2. So this is even simpler to calculate, because you can just subtract row 1 from row 2 and row 3. So here the only equation that we have two x minus y minus 2z equals 0. Okay, so that's the only equation that we get. And hence, check that E1 is given by span of the following two vectors: 1, 2, 0 and 1, 0, 1. Okay. Then the last thing to check is that this set 1, 2, 0 and 1, 0, 1 is also linearly independent. Okay, hence it forms a basis. So the dimension of E1 is 2, and we are good. So for each eigenvalue, we have that the geometric and the algebraic multiplicities, they match. In this case, they are both 1, and in this case, they are both 2. Hence, we conclude that the matrix is diagonalizable. And we are almost complete with the diagonalization process. So the D, matrix D, or at least one choice of matrix D, is simply writing down the eigenvalues. So 1 and 1. So count this 1 twice. So it has the algebraic multiplicity 2. So this is the diagonal matrix. Okay. And then accordingly write out P. So the first column would be the eigenvector corresponding to 0, which was, I believe, 1, 1, and 1. And then the eigenvectors corresponding to the eigenvalue 1. Now here, the thing is that you have a choice of writing out the two vectors. We have chosen 1, 2, and 0 to be the first vector in this set, and 1, 0, 1 to be the second vector. So then you write it down accordingly. So 1, 2, 0 and 1, 0, 1. But remember that you can also flip. So you can flip 1, 0, 1 and 1, 2, 0. So 1, 0, 1 could be your second column, and 1, 2, 0 the third column. And it will give you the same equation. So we have 0, 0, 0, 0, 1, 0, 0, 0, 1 equals 1, 1, 1, 1, 2, 0, 1, 0, 1. Inverse, then A times 1, 1, 1, 1, 2, 0, and 1, 0, 1. Okay, so this is one diagonalization. Of course, you can switch the zeros and ones in the diagonal and accordingly change the matrix P. So, but the main thing is to obtain 1D and 1P. Any questions about this particular problem? I mean, this is a slightly elaborate version in 2x2 scenario. That's it. So is it absolutely clear what's going on? I mean, we are just putting the algorithm into practice. That's it, nothing else. Okay, so then let's move on to something else. Where are we? Just a moment. One particular thing, let's take it as a fact because we will use this in certain problems. And I think we have mentioned it before. So let B be P inverse AP. So A and B are similar. Then we have shown means we have shown up to a point that B to the n is equal to P inverse A to the n P, right? So it's only the power of A that matters. Now, so this is the point, if a matrix A is diagonalizable, then it's easy to compute the powers after diagonalizing. In the sense that if D is equal to, let's say, P inverse AP, where D is a diagonal matrix, then from this formula, D to the n is P inverse A to the n P. Hence, A to the n is simply P D to the n P inverse, right? And computing D to the n is fairly simple because D is a diagonal matrix, and hence any power is simply taking the power in the diagonal entries. So computing D to the n is simple since we are taking nth powers So we are just taking nth powers of the diagonal entries. So this is something we will use for certain problems to compute powers of a matrix. Okay, so just to, for example, here, so let's solve this. Find A to the 50, where A is the matrix we have worked with before. So 2 minus 3, 2 minus 5. So this is our A. And so I'll just say that we know that A is diagonalizable. In fact, we have that 1 minus 4, 0, 0. So from the first problem equals, I think, 3, 1, 1, 2 times A, or rather inverse. Okay, so this was the diagonalization. And hence A is given by 3, 1, 1, 2 times 1, 0, 0 minus 4, and 3, 1, 1, 2 inverse. And by the previous fact, A to the 50 is given by 3, 1, 1, 2. Then you take the 50th power of this diagonal matrix, but It's just taking the 50th power of each diagonal elements, and of course 50th power of 1 is 1, and this is simply 50th power of 4, because 50th power of -1 is 1, 0 and 0, and then 3, 1, 1, 2, inverse. Okay. Now here is at least one visible advantage of diagonalization, because computing powers of matrices is needed. And a priori, if you don't know diagonalization, then computing powers of such a matrix, it's an arbitrary matrix with some entries. So computing powers of this matrix would be a horrendous task. I mean, I don't know, maybe even computing the 10th power of A would be a hard task. But from this much simpler process of diagonalization, I mean, what you do is just find the eigenvalues and the eigenvectors and the matrices D and P, which is doable. I mean, that's just doable with pen and paper. You don't need a computer. And then the whole process reduces to this particular multiplication. And this multiplication you can do by hand, just by hand. Well, of course, 4 to the 50 is a huge number. But this is the beauty of this diagonalization. It reduces this apparently hard problem of computing powers of certain matrices to a much simpler problem of multiplying 3 matrices. Well, computing the inverse, which is, I mean, it's a 2x2 matrix, so finding the inverse is not hard. Okay, so that's one very visible use of diagonalization. Okay, so once again, any questions about it? If you have the lecture notes, then I mean, everything is there. Okay, good. So there are no questions. So then let's move on to something, I mean, some examples where matrices are not diagonalizable. So this is number 2 from defective matrices. But I will just say number 4 because we did 3 problems before. So something like this. So is this matrix is A diagonalizable? Okay, the first thing, without going into computing the characteristic polynomial or anything, can you tell me right away what are the eigenvalues of this matrix? Or not looking at the lecture notes. So what are the eigenvalues of this matrix? Any guesses? No guesses? Two and four, exactly, good. 2 and 4, yes. And what's the multiplicity, algebraic multiplicity of 2 and 4?
Can you go over how you know that without getting the polynomial?
So what's the algebraic multiplicity of 2? It's 2, right? And that of 4 is 1. So at once, we can say that the eigenvalues are lambda 1 equals lambda 3 equals 2, and lambda 2 equals 4. So just to emphasize the position, the first and the third position is that of 2 and the second one, it's just a way of naming. So this one has algebraic multiplicity 2, and this one has algebraic multiplicity 1. Well, okay, now whenever you are asked such a question that whether A is diagonalizable, the first thing would be to leave out all the eigenvalues whose algebraic multiplicity is 1, whose algebraic multiplicities are 1, because you know that the eigenspaces will have the eigenspaces will have dimensions at least 1, and since the geometric multiplicity cannot be more than algebraic multiplicity, it has to be 1, exactly 1. So for eigenvalues whose algebraic multiplicity is 1, algebraic multiplicities are 1, the corresponding geometric multiplicities would be 1. So you can leave those out and concentrate on those eigenvalues whose algebraic multiplicities are more than 1, because that's when the problem might arise. I mean, the geometric multiplicities might drop. So in this case, let's check the eigenspace for 2. So let's, well, at least for this problem, let's write out the reason. Since lambda 2 equals 4 has algebraic multiplicity 1, we know that the geometric multiplicity of 1 has to be 1. So remember that geometric multiplicity is less than or equal to algebraic multiplicity. So we check for lambda 1 equals lambda 3 equals 2. Okay. So basically the eigenspace corresponding to 2. So E2 is the null space of A minus 2I3, which is fairly simple. So A has entries 200, 040, 102. So if you subtract 2 from the diagonal elements, you are left with 000, 020, and 102. Sorry, not 2, but 1, 0, and 0. Okay, so what does this mean? It means that the corresponding solution is fairly simple. So 000, 020, 100 times xyz, if this is equal to the 0 vector. From the second equation, what you are getting is that y equals 0, and from the third equation, you are getting that x equal to 0. So this means that 0 times 2y times x equals 000, which further means that y equals x equals 0. Okay. And finally, what you get is that E2 is given by this set such that x and y are 0. So basically this is span. So the only non-zero component is the last one. So this is span of 0, 0, 1. Okay, which means that the dimension of E2, which by definition, this is the geometric multiplicity of 2, is 1. Okay, and since 1 is less than 2, we get that A is not diagonalizable. So this is a particular example where instead of trying to check whether A has a basis of eigenvectors or not, you work with the algebraic and the geometric multiplicities. So here we check that the geometric multiplicity of 2, geometric and the algebraic multiplicities of 2 doesn't match. And you can say at once that A is not diagonalizable. Okay. Clear? Any comments or questions? Okay, seems clear. By the way, some of you told me about, or one of you told, so when I'm writing on this page, should I sort of keep half of this page visible? That's what somebody was saying. As long as possible, I guess. So from time to time, of course, I'll forget, but I will try to remember. Okay, so that's an example of a matrix which is not diagonalizable or defective, if you want to call them that, defective. Okay, so let's move on to something a little bit more involved. So we are so we will solve this problem. Let's go to, okay, one quick question. So this is very short answer. So one line, is this matrix diagonalizable or not? Any ideas? We have seen, well, not similar problem, but at least you should be able to tell me the eigenvalues right away. So what are the eigenvalues? Two, 6, and 1, exactly. So Terrell is right up to, yeah, so he is in terrific form today. Okay, 2, 6, and 1. Then somebody else. So is it diagonalizable or not? What can you say? So yes, because, okay, because it has 3 distinct eigenvalues. Great, so this is somebody, Cuadres. Great, good answer. So I think you guys are just letting Terrell answer. I mean, it's his day, maybe. Exactly, so it has 3 distinct eigenvalues. So it has 3 distinct eigenvalues, 2, 6, 1, hence from a fact, so I'll just say from a fact done before, this is diagonalizable. Good. So then let's see which problem we can do. Okay, so this is a variant of finding powers. So which problem here? So this was 4. This would be 5. So this is a variant of finding the power. So here you are given the following matrix: A 2 1 minus 2 1 minus 2 minus 1. Sorry. So now find a matrix B such that B square equals A. So it's something like finding a square root of a matrix, right? So you can more or less write that B is the root of A in terms of matrices. It's not completely accurate, but up to a point, let's say. So you're using the same, you will use the same trick. First of all, check that A is diagonalizable or not. So then let's write down the idea. Check if A is diagonalizable or not. It is. Of course, that's what the problem is based on. So check that D is given by the following matrix. So D is given by, so these are the two eigenvalues, 0 and 1. So then you have D, and then your P is given by, let's see, 1 minus 2, 1 minus 1. So 1 minus 2 is the eigen, so let's, so the eigenvalues. So this is where I'm skipping some steps. Eigenvalues are lambda 1 equals 0, lambda 2 equals 1. Then E of 0, check that this is given by span. Oops. So this is given by span of 1 minus 2 and E of 1. So this is given by span of 1 minus 1. Okay, so these are the eigenvalues and eigenvectors. So hence we have the D and the P. So you have A equals this part, 1 minus 2, 1 minus 1. So this is P. Then D, 0, 0, 0, 1. And the inverse. So 1, 1, minus 2, minus 1, inverse. Okay, so this is the diagonalization part. Now, here is the main point. The main point is the following. So this is the D. So easy to see. So this is the easy part, easy to see. Right, so D square is D because it's a diagonal matrix and the diagonal entries are, they satisfy similar properties. So if you take the power, so any power of D gives you back D, okay? So then what you can write is the following. So A is equal to, so let's give this matrix, well, we already have the name, so P. So A is P D P inverse with this knowledge that D square is equal to D. So we can rewrite this as P D square P inverse. Okay. Now using this property that this P D square P inverse, this is P D P inverse square, right? So remember that something like P A P inverse to the n. So this is P A to the n P inverse, right? But what is this PDP inverse? It's A. So finally, what we get is that A is same as A squared. So the square root of A is A itself. Slightly surprising maybe, but you can check. I mean, you can directly check by taking the square of A that you will get back A. But I mean, this is a very concrete process of finding out the root. So you can apply this to any diagonalizable matrix. Okay. So let's write down the abstract. So the abstract process is the following. So let A be a diagonalizable matrix find B such that B to the L equals A. So suppose you have some problem like this. You want to find the Lth root of A. So the general technique is diagonalize A. Okay, so let A be equal to PD P inverse, where D equals the diagonal matrix. So lambda 1 up to lambda L, okay, and zeros everywhere else. Then the idea is that find, let's say, D prime such that D prime to the L gives you D. So in this case, D prime is given by taking the Lth root of each, oh, sorry, so this would be, so we are working with n cross n matrices. So you take the Lth power of each entry in the diagonal. So then, of course, D prime to the L will be D, okay? And then you have A equals P D P inverse. So this is P D prime to the L D inverse and equal to, so this can be written as P D prime, sorry, P inverse to the L. So then this particular matrix is your P. Okay, so this is the general technique. Whatever power you want to find, you should use the diagonalization method. Okay, so that's a general method to find out the roots of A, let's say. So any question about this abstract method? It's exactly similar to this case, just that you were generalizing to some L. So L, let's say, greater than or equal to 2. Okay, so is it clear? I mean, this is not covered on the lecture note, but I thought that I will give you the general formula. Okay, so let's move on. 3 goes through matrix. Okay. Okay, so this is something which you might face from time to time. So this was problem 6. So you will be given some unknown values. So find. So we are right now at page 22 of Eigen 4. Find all possible values of alpha such that this particular matrix, so A is 1, 1, 0, the first two rows are same, and the third row is 0, 0, and alpha, okay, is not diagonalizable. Or let's say diagonal, well, just to change the problem a little bit, is diagonalizable. Okay. So let's, okay, so the point is to find the eigenvalues first. So the eigenvalues would be in terms of alpha. So then this is the determinant of A minus lambda I3. And now check that the polynomial would be the following: lambda minus alpha times 1 minus lambda minus 1 square. So this is the polynomial, and hence the eigenvalues lambda 1. So these are the three eigenvalues. Lambda 1 equals alpha, lambda 2, so lambda 2 equals 2, and lambda 3 equals 0. So these are the three eigenvalues. Okay. Now, case 1. So we have to study case by case. So case 1, if alpha is different from 2 and 0. So what can you say? If alpha is different from 2 and 0, then what would be the conclusion? Yes, why is that diagonalizable? So it has three distinct eigenvalues then, exactly, three separate eigenvalues. Then using, since then A has three distinct eigenvalues, hence is diagonalizable. So that's the easy part where alpha is different from 2 and 0. So now case 2. Now alpha can be either equal to 2 or equal to 0. So let alpha equal 2. Okay, so that's the second case. So then what is the matrix? If alpha is 2, then A is given by the following matrix: 1, 1, 0, 1, 1, 0, and 0, 0, 2. Okay. And then if you find the eigenspace, and another thing, if alpha is 2, then lambda 1 equals lambda 2 equals 2, and lambda 3 equals 0. So once again, we don't bother about the eigenvalue 0, because the corresponding eigenspace will have a geometric multiplicity 1. So we don't bother about that. So that is not our concern. Our concern is the one with eigenvalue 2. So this has algebraic multiplicity 2. So we need to check the eigenspace. Okay, so let's find E of 2. So this is the null space of A minus 2I3, which is given by the null space of the following matrix. So minus 1, 1, 0, 1, minus 1, 0, and the third row is all zeros because the last entry is 2, so it's all zeros. So then check that this is given by span. I mean, it's fairly simple to check once again, because you just add row 1 to row 2. Then row 2 becomes all 0. So the only equation that we have is given by x minus y equals 0, or x equals y. So that's the only equation we have. And z is the free variable. So then it's given by the span of the following two vectors, 1, 1, 0. So 1, 1, 0 coming out from this equality, that x equals y. And then you have the other eigenvector, 0, 0, 1. So this comes from, so this 1, 1, 0 corresponds to x equals y, and 0, 0, 1, since z is free. Okay. Oops. So it means that the dimension of E2 is 2, hence, or let's see. So this is equal to the algebraic multiplicity of 2. Hence, in this case, A is diagonalizable. So that's case 2. Now, the only case left is the third one. So then the last case is alpha equals 0. Okay. So then we have that lambda 1 equals lambda 3 equals 0, and lambda 2 equals 2. So 0 now has algebraic multiplicity 2. So this one has algebraic multiplicity 2, and this one has algebraic multiplicity 1. So we don't, once again, we don't bother about this eigenvalue. So we need to check the eigenspace corresponding to 0. Now the matrix A is even more simple in this case. So it is just given by 1, 1, 0, 1, 1, 0, and the third column is already 0. Okay, so then E0 is simply the null space of A. So null space of this matrix, 1, 1, 0, 1, 1, 0, and 0, 0, 0. And of course, just in one line, you can check that if you subtract row 1 from row 2 is all 0. So you have x plus y equals 0, and z once again is free. And hence, this is given by span of now 1 minus 1 and 0. So this coming from this equation, x plus y equals 0, and 0, 0, 1 coming from the free variable. And hence, dimension of E0 is once again 2. So this is equal to the algebraic multiplicity of 0. And we conclude that A is still diagonalizable. Okay. So the final answer is that A is diagonalizable for every real number alpha. Okay, so for each value of alpha, A is diagonalizable. So you might face problems like this, and depending on the matrix A, either A would be diagonalizable for each and every alpha, or there might be some specific values of alpha for which A might not be diagonalizable. The important thing is to do this case by case. So, I mean, all the time you will know most of the eigenvalues by numbers. For example, here you know these two eigenvalues, lambda 2 and lambda 3. They are 2 and 0, so they are fixed. What varies is the first one. So depending on the choice of alpha. So you have to separate out cases to conclude whether it's diagonalizable for every alpha or not. Okay, so that's sort of a standard way to solve this sort of problems. There might be more than one variables. So I'll put some problems in the practice problem part where you might have an alpha here, maybe a beta at some other place. So then the eigenvalues would be slightly more complicated. It will involve alpha and beta. So then you need to do a little bit more work to figure out when it's diagonalizable or not. Okay, so any question about it? So this sort of question is slightly more involved. So you need to work a bit more to do it. So any questions? Is absolutely clear? In the lecture note, initially, well, it happened, I think, in one of the classes, I did it wrong. So that has been corrected. So this check next page on page 23, so we are still in eigen 4. So check next page. So here, the correct computation for alpha equals 0 is done. But anyway, so this is the main point. So you need to do case by cases. Okay, so what I plan to do right now, so eigen 5, it consists of problems, more problems on eigenvalues and eigenvectors, diagonalization. So more varied type of problems. So what I want to do is the following. So I will treat eigen 5 once again as a set of practice problems. And you should look at them and ask questions during office hours or otherwise if there are some specific problems you want me to discuss. And I will do that maybe in some office hours. But now I want to move on, maybe for the last 5-6 minutes, to vector calculus. So we are ending this part on the linear algebra. We have done enough problems of varied types, and there are more on the lecture notes. So study them as much as you can, and you can ask questions anytime and we can discuss. But now I want to move on to the next part, vector calculus, just to start off today. Before we go, anything else about these problems that we solved? Okay, so let's move on a little bit to vector calculus. We will begin with this lecture 1. So vector calculus 1. So this is more or less a review of differential calculus and some examples. Before we begin, the way I wrote it down is fairly elaborate. So I covered something related to limit of sequences of real numbers, then limit of a function, then continuity of functions, a little bit about something called topology of a real line, which, I mean, this term topology, you don't need to bother about too much. You need to know a little bit about this completeness theorem of Cauchy, then maybe Bolzano-Weierstrass, the basic definition of derivative of a function, real valued function, then some differentiability theorems, and properties of differentiation like chain rule, quotient rule, things like that. Then derivative of inverse function, then properties of differentiable functions. So Fermat's last theorem, Rolle's theorem, mean value theorem. So up to page 10, so if you look at the lecture note, up to page 10, so how many of you want me to go through it, or you want to study them on your own, or some of you know most of them? So I can just start from vector valued functions. So that will save some time. It's up to you. I can discuss pages 1 up to 10, or I can leave it to you to read and just start from vector valued functions. So what do you want? It's up to you. So starting from vector valued functions, we can maybe do a little bit more. Okay. So let's do the following. Let's start from vector valued functions, and once again, keep pages 1 to 10 for self-study, and ask me questions during office hours or otherwise, and I will try to clear off any doubts that we have. Because the point is we will mostly use maybe from time to time some properties from page 1 to 10. So in some sense, there's no point in going over very thoroughly about these properties. Just you need to know them. So let's start from the definition of vector valued functions. So even before that, so let V1, so this, we are in page 11 of the note, etc. So a sequence. So we have a sequence of vectors in Rn. So each Vi or Vk, if we follow the note, so each Vk is a n vector. So x1k, x2k, xnk. So each Vk is an n vector. So we say that this sequence, so V1k, oops, this converges to a vector u. So u is another vector un if, so this is if and only if statement, each xik converges to ui. Okay, so each component converges to each component of u. Okay, so that's the definition of being convergent in the sense of a sequence of vectors. Okay, so that's something which we need to get out of our way. So then a vector valued function v. So this is from x to Rn, where x is a subset of R. So we take a subset of R. So x is typically an interval of type AB, AB, and okay, so we will typically consider such intervals as x. So x is a subset of Rn. So it's a vector valued function is a collection. What's going on? It's a collection of real valued functions. So fi from x to r such that the following, such that for 1 less than or equal to I less than or equal to n, v at t equals f1t, f2t, fnt for all t inside x. So this is a vector valued function. So it's a real valued function on each component. That's it. So we say the following. So we say that v is continuous. Oops. At each t if the individual functions fi t are continuous at each t belonging to, oops, not 12. Okay, for each t belonging to x. So, I mean, a vector valued function is defined through functions of real variable, basically. So on each component, this f1, f2 up to fn, these are real valued functions. Typically, we have the following examples. So now the examples are later on this lecture note. So if you go to page 24, you will find some examples of vector valued functions. So examples of vector valued functions. And we will stop with the first one. So there's an image of how a vector valued function looks like. It's typically a path of a particle. So think, it's better to think such examples in terms of physics or like vectors in physics. So it's a particle moving along this path. So if you go to page 24, you have this picture that Vt is F1. So the picture is in R3. So we have Vt as F1, F2, and F3. So it traces out the path of a particle traveling along this sort of weird movement. Okay. So for example, the typical thing to start off is a line. So lines in 3D. And lines in 3D, we know that they can be written in different ways. So they can be written in vector equations. They can be written in coordinates. And now let's write it down in terms of a vector valued function. So we have this line. So take the line. So starting at this point P equals 1, 3, minus 2, and moves towards this point Q, which is 2, 1, 3. Okay. Then the direction vector P to Q is given by subtracting. So it's basically the vector Q. Let's use the, so this is 1, minus 4, and 5. And hence this equation V from, so now our X is the real number, so R from R3. So this is our X in this case, is given by V of T. Well, the point is you have to determine. Let's say X is R for the moment. So this is V of T. So it's equal to P plus T times 1 minus 4 minus 5. Okay. And if you write it down, this will give you 1 plus T, 3 minus 4T, and minus 2 plus 5T. Okay, now this is the general equation. The point is that this will also determine what X is. Notice that you have to start from T equals 0 to start from the point P, right? So then X here in this case is, so you start from 0, and at T equals 1, this is Q. So X is actually 0, 1. So this is a subset of, well, this is not R anymore. So this is, let's write it down. So you're taking this interval 0, 1 and mapping it to R3. So that will give you this line starting from P and ending at Q. So typically this is how you parameterize. So this is called the parametric equation. So this is called the parametric equation of the line, of the given line. Okay, so that's one example. Oh, okay, so we had a long class. So it's a good point to end here. So next day we will continue with examples and do some more properties. The idea is to start off vector fields and scalar fields as soon as possible. Okay, so that's where we end today. Parametric equation of this line, starting from P and ending at Q. Yeah, so it's the parametric equation of the line. It's not explicitly written on the lecture note, but that's what it is. So this is the parametric equation of the line starting at P. Oops. And ending at Q. Okay. Anything else? Scroll up a little bit here. So examples of vector valued functions or more? Oh, it was just the last part, okay. Okay, good. Okay, so if there are no more questions, then I will end here, have some coffee, and come back at 4. Yeah. See you next class. So you want to do the same class twice? Okay, so see you anyway. Oh, next class on Thursday. Sorry, my bad. Okay, bye for now. Bye-bye.